Hi everyone. In this video we're going to talk about chapter 4, which begins our discussion on continuous random variables and probability distributions. Now what we'll go through, and we'll just get to the PDF part this time, is what is a PDF. Okay, and so we're going to move from PMFs to PDFs, and that's a sort of a big change. Then we'll talk about the CDF of a continuous random variable and moments like the expected value, so on and so forth there. And then we'll get into specific probability distributions. And so we'll talk about the normal, which is the most important one. And then we'll talk about two more called the exponential and gamma, and we may talk about a few others as well. So what we've done so far in this course is talk about discrete random variables, which are random variables that are counting a finite number of things. Okay, or I'll call them countable number of things because it could be countably infinite. But anyway, unfortunately, that doesn't encapsulate all of the random occurrences in the world. Excuse me. We may have instances where random variables represent an uncountably infinite number of possibilities. And so here are some examples. So I could be measuring or making depth measurements at a certain lake at randomly chosen locations. I could be measuring a chemical compound, or I could select a chemical compound and I could measure its pH level. Okay? Or I could be selecting the amount of time that a randomly selected customer spends waiting for a haircut. All of these examples are all of these situations are examples of continuous random variables. They are technically or theoretically the outcomes of making these measurements is infinite, and it's uncountably infinite number of possibilities. And now you may balk at that statement, and many people rightly do, and the book actually gives a paragraph or two about this, that even though the instruments that we use to measure this, like taking that depth measurement or measuring the pH level or measuring the amount of time, none of those have a technically infinite level of precision. And so what are we talking about when we are discussing continuous random variables? The random variable has a theoretically uncountably infinite number of possibilities. And so, but what are we doing? Really, in these three examples, we're just counting. We're not really counting things, but we're making like a depth measurement. And so you may say, well, if I'm measuring it in meters, I'm probably only like 1 meter, 2 meter. At most, I'll go down to maybe 2 decimal places, but that's still not uncountably infinite. That's not quite there. I could still just count all the different types of decimals if I only go to 2 decimal places. Similarly with the pH level and the amount of time. Usually I'm going to tell you maybe like 10 minutes or 10 minutes and 52 seconds, but I'm not going to go down to an infinite level of sort of time precision, because none of the things that we have to measure time can do that, or pH level, or a depth measurement. So, although measuring instruments for these situations, we can't get to that infinite precision that we want, continuous situations often approximate those discrete situations, which means that they do a good enough job. And it turns out that what we're going to use to find probability in continuous situations is calculus, and calculus is often easier to work with than sums. Okay, so basically we're going to do a good enough job with continuous situations because it's easier to work with them. So how does that sort of happen theoretically? Well, if we view and think of this as our first example, where we're measuring the depth of the lake in in meters or something like that. Okay? In figure A, they say this is a probability histogram of depth measured to the nearest meter. And so what they mean by the probability histogram is, if you remember, in any visual that we looked at of a PMF, we had this probability at a point, and so they were like lines up at the single points. Well, we can extend those lines and make histograms where each of the histogram bars are centered at that point. And so you'll see in sort of the left side here, we've got a bar that's centered at 0, and then it's going to be a bar centered at 1, 2, 3, 4, 5, and then all the way up to M. Okay, but it's not the histogram is not really counting anything between the numbers. Okay, if we consider that, let's say this would be 1, 2, 3, 4, 5, and we'll say instead of M, we'll say 6. Each of the bars are centered at the number, and we know that there's no probability in between those numbers. And so even though the histogram technically binds together lots of different numbers, and you may not even know what a histogram is, so what I'm saying doesn't sort of make sense, but hopefully you do. It's okay to have a histogram this way. Each bar represents the probability that single thing happens. Okay? So by what we know about PMFs, we know that all of the bars have to add up to 1, or the heights of the bars all have to add up to 1. And so that's why this thing is called a probability histogram, is because the thing on the y-axis are probabilities. Okay. So now the question is, what if we add more in? So what if we measure now not to the just nearest meter, but the nearest centimeter? Okay, and so that's going to create a probability histogram with many more bars, as we see in the middle. And then we can just continue that argument and go down, keep going and keep going and keep going until we have a ton of bars, and each of the bars are like barely any width. And so that's the idea to get from if we can go to infinite precision, then technically we're going to have an infinite number of bars that each have like no width to them. And then that gets us to what we're going to call a density, which is sort of the jump from the second one to the third one. And so a density represents continuous stuff. And so in the description here, it says the limit of a sequence of discrete histograms. So technically that means we're taking a limit in the calculus sense, but we don't really need to worry about that right now. We can approximate these bars with a continuous curve. And so that's what we're sort of doing here. And so instead of having points like we did with discrete variables, we now have a curve. Okay, so it may be a nice curve, it may be not a nice curve, but we have a curve, and then that is going to represent probability for us. And we'll see how that works in just a second. So for a continuous random variable, so now we're going to talk about PDFs. Okay, and so for a continuous random variable x, the PDF of x is a function like any other function. So always think this is, try to compare this with the PMF, okay, because they are the same thing. So PDF and PMF are sort of serve the same role, but for different things. Okay, so they serve the same role, but PMF is for discrete, PDF is for continuous. Okay, so think of those two things together and compare and contrast as I'm talking through this. So continuous random variable x, it's going to have a PDF, or probability density function. It's a function f, just like any other function, and we define the PDF this way. So for if I'm looking for the probability between two numbers, so if I'm looking for the probability that x, the random variable, is between a and b, what I do is I take the integral of the PDF from a to b. Okay, so that's how you define a PDF. It's a function such that if you want to find the probability that x is between two numbers, you take the integral of the PDF of x between those two numbers, a and b. So what does this mean in words? It means that the probability that the random variable x takes on a value between the interval a and b is the area under the curve of the PDF. So remember from your calculus days that integrals calculate area under a curve. And so that's really helpful for us because we now have a curve or density that represents probability in some way, and turns out that we can get the probability that x is between two numbers by just taking the integral of that PDF between those two numbers. Okay. And so visually, this is what it looks like. So I have that curve, and so to find the probability between those two numbers, I find the area under the curve between those two numbers. All right, so for f of x to be a valid PDF, it must satisfy the following two conditions. And so again, if you remember back to the PMF, we also had two conditions that it needed to verify. And the first one looks very similar, that the function needs to be non-negative, so 0 or more, for all possible x. Okay? And so this means now that the curve must be above 0 for all x. Before we had like discrete x values and it had to be true for each of them. Now we have a curve. It means that the curve must be above 0 at all times, or hit or be above 0 at all times. And the second one is that the integral from negative infinity to infinity of the curve, okay, of the PDF must be equal to 1. Okay? And this is like the sum to 1 condition for discrete random variables. So before, I had to add them over all x, right? I'd add up all the PMF values over all x, and those PMF values had to sum to 1. Well, now I have to take the integral over the PDF, and it needs to be 1. Okay? Negative infinity to infinity encapsulate everything for a continuous random variable. Okay, sometimes it may not be plausible that x values could be infinite, but that just means that the probability there is equal to 0, and so it doesn't matter. But anyway, so these are the two conditions that we need to satisfy, and so we'll have practice satisfying these conditions. Now, this raises a number of important differences that you need to keep track of when we're talking about discrete and continuous random variables. And so the first one is that all of the sums are going to change to integrals. So before we had sums that we were working with, capital sigma. So the sum over all f of x is equal to something. And now we have the integral over f of x equals something. Okay? So all the sums change to integrals. And then this is a really important one. And so this gets to a lot of theoretical stuff about the continuous random variables that you need to be aware of. And it says that for any number a, the probability that x equals that number is equal to 0. Okay? So for any point, no matter what that point is, the probability that that point is that the random variable equals that point is 0. And so a way to say that in words is that there is no probability at a point. And this is totally different from what we're used to with discrete random variables, because at discrete random variables, probability only happened at a single point. Right? If I had values for, I was rolling a dice and I was looking at the value of the face of the dice after it was rolled. It was 1, 2, 3, 4, 5, and 6 are the possible outcomes, and the probability only happened at those points, right? To be technical, they should all be the same height. But the probability that it landed at 1, that was the only probability around it. At 1.1, it was 0. At 1.5, it was 0. Everywhere else except for those points, it was 0. But at those points, there was actually probability. With continuous random variables, it's the exact sort of opposite. There's no probability at a point. There's only probability in an interval. So probability is only defined within some interval. And so there's a bunch of arguments, not an actual argument between things, but an argument for this. And the book makes a couple of different ones. It makes a physics kind of argument, and so if you tend to be swayed by those, I'd suggest you read this section 4.1 in the book. But what it really means, or what you can think of, the random variable that I often go to in these situations is running a marathon, maybe, right? And so if I said a marathon usually takes, if you're really good, I think we'll say 4 hours, right? And so it could take anywhere from 4 to 12 hours, and maybe they cut you off after 12. And so the question is, if I run, and that's and we'll say I can measure down to infinite precision. I can measure, it took me this many hours, this many minutes, this many seconds, this many milliseconds, and this many, so on and so forth, as far as we can go. What's the probability that, say, I ran the marathon in 7 hours, 8 minutes, 10 seconds, 15 milliseconds, and then I just keep on going, an actual number? So what's the probability that you actually do that in real life? And the answer is probably really close to 0. If I go down to an infinite number of things, the probability that I run it in, or say exactly 5 hours, 5 hours on the dot, but at infinite level of precision. So if you miss it by a millisecond, but if you miss it by, what's ever lower than a millisecond, you're off. You don't round, there's no rounding, and so, what's the probability that you actually reach that? And the answer is 0. It's not going to happen. Now, there's a difference between this 0 and not possible. So this means that it's not going to, it's the probability that happens is 0, but that's different from being not possible. So it is possible for me to run a marathon in 5 hours exactly, down to an infinite level of precision. That is possible, but the probability that it happens is 0. That's different than me being able to, than something that is not even possible. And so there's a difference there, and we really don't need to talk about it too much, but I thought I would mention it. A more convincing argument maybe is that if I'm looking for that exact point on, say, a density function, so I have a curve, I have some curve here, and I want to find probability at a single point A. How would I find that area there? Well, it's an integral from A to A of f of x dx. The integral from one point to the same point from A to A, whatever A is, that integral is 0. And so there's no probability at a point. Okay, so I've probably belabored that point longer than it needs to, but that is an important distinction that we need to make between discrete and continuous. Now, this also has another important consequence, and it's something that we harped on a lot for discrete, the difference between less than and then less than or equal to. So we had a lot of pains of inclusive and exclusive, what that means, how that changes. For continuous random variables, it doesn't matter. So it doesn't matter if it's less than or equal to, it just doesn't matter. So whatever the problem says, it doesn't matter, because there's no probability at a point. And so those less than or equal to, and less than are the same, because there's no, for the previous point, that there's no probability at a point. So whenever you see a continuous problem and you see less than or equal to or less than, you don't need to freak out. Just do the problem and don't care about the inequalities. If you have a discrete case, then you do need to worry about the inequalities. But here, you don't. All right, so anyway, let's actually work with a PDF. So here's an example directly from the book. The direction of an imperfection with respect to a reference line on a circular object, such as a tire, brake rotor, or flywheel, is in general subject to uncertainty. Okay. Consider the reference line connecting the valve stem on a tire to the center point, and let x be the angle measured clockwise to the location of an imperfection. Okay, so one possible PDF for x is this function. Right? So it doesn't really matter to me whether you find a connection with the example itself, because I certainly don't, but still we have a PDF, we can work through it. So first question, prove that this is a valid PDF, and then second question, find the probability that the angle will be between 90 and 180 degrees. So the first thing that we need to do, valid PDF. Valid PDF means that f of x is greater than or equal to 0, and the integral, I can't draw an integral sign here, from negative infinity to infinity of f of x is equal to 1. Okay, so it's easy to look and see that up here the values of f of x for all x is non-negative, because it's it's 1 over 360 when x is between 0 and 360, and it's 0 elsewhere. So first one, great, check. This one is easy. It may be, or it will be, not so simple for other examples where you don't have a constant. Here you have an actual function. But anyway, we'll bask in the easiness for now. Great. And then integral from negative infinity to infinity of that function is equal to 1. All right, so let's do it. Integral integral from negative infinity to infinity of 1 over 360 dx. Negative infinity to infinity is not easy to work with, but if we look at our PMF up here, we'll see that it's positive. It's 1 over 360 only when x is between 0 and 360. So instead of taking the integral from negative infinity to infinity, that's the same as taking it from 0 to 360. Those two are the same thing, because elsewhere, below 0 and above 360, really at 360 and above, the probability is 0. So I only care about between 0 and 360. And that's a lot easier to work with. Here we have a definite integral, and so we find the antiderivative of a constant, and the antiderivative of a constant is x times that constant. So really we're the integral from 0 to 360 of 1 over 360 is take the antiderivative, right? And we get x over 360, and you define it from 0 to 360. You plug in 360 and you plug in 0, or you substitute those in, and you get 360 divided by 360 minus 0 over 360. And so that's 1 minus 0, or 1. And so lo and behold, integral from negative infinity to infinity is 1, and so that's sort of checked as well. Okay, so hopefully you're able to follow along there. You have to remind your mind of what integrals are, how to sort of do them. We'll always deal here with definite integrals. We're never going to just like add the plus c. And so, okay, second part, with what space we sort of have left here. The probability that x is between 90 and 180. Okay, between 90 and 180, again, it doesn't matter what the inequality signs say. And so now we take the integral from a to b, so the integral from 90 to 180 of 1 over 360 dx. You need to solve that integral. Again, definite integral. We take the antiderivative. We get x over 360 evaluated at 180 and 90. And sorry, my things are sort of coming together there. But anyway, we substitute in 180. We get 180 over 360 minus 90 over 360. And that's equal to, when you do the math, it's equal to a quarter, or 0.25. 0.25. Okay, so hopefully that wasn't too bad. It turns out that this example, where we had a constant as our PDF, is a special example called the uniform distribution. Okay, so and a random variable x is said to have a uniform distribution on the interval a to b if the PDF is of this form. So the last example was 0 to 360. The PDF was 1 over 360 minus 0, which is 360, from 0 to 360. When a distribution looks like that, it's a uniform distribution, a continuous uniform distribution. And it has sort of the nice picture below. It's a straight line where you have positive probability, straight horizontal line, and then 0 elsewhere. And what's especially nice about the uniform distribution is if you really hate calculus, you can draw it out and then just use sort of algebra skills and or maybe geometry, that you know the area of a rectangle. You know the height of the rectangle is 1 over 360, and you know the area for our specific example was 90 to 180, and so that means that the height is 1 over 360, the width is 90, and so there you get your area just doing regular geometry sort of things. Usually you have to use calculus when it's not the uniform distribution. So last one. Finally, we get to your turn. I give you an example here. The example is uniform. Okay, and so walk through the example, prove that it's a valid PDF, and find the probability that the bus will be between 5 and 8 minutes early.